All right, welcome back to part two of our lesson on the coordinate plane and function symmetry. Strap that seatbelt in because it's going to be a bumpy ride. So on this slide here, I would like for all of you to simply organize the graphs in any way you see fit, focusing on graphs displaying similar tendencies. As you sort, we encourage you to look at the behavior of the entire graph rather than focusing on specific points. After you do that, I'd like for you to kind of describe your rationale in grouping the functions in the manner you did. What were the similarities and differences that you noticed, and how did they play into your schema? What I was asking you to categorize and group together were what we call even and odd functions. That is very different than the degree of a function. Remember, the degree is the highest exponent. So we would say that the function has a degree of 2. Many people get lazy and say, oh, well, that's an even degreed function. But it is not. We can't assume that a function with a degree of 2 is necessarily even. Even functions are functions whose graphs look the same when reflected across the y-axis. Don't know why that's not working. Okay. And odd functions are functions whose graphs that look the same when reflected across the x and y axes. Now that you're aware of this information, you might want to go back to the previous slide and reorganize your cards with those two thoughts in mind. Okay. For this graph here, I'd like for you to match each table of coordinate pairs with one of the graphs. I will match these two together because it is apparent that for a constant, right, a graph that is a horizontal line, all the y values will be the same. So please match up your graphs in a corresponding fashion, so on and so forth. Clearly that is not correct because I have a counter here for you. After doing that, I would like for you to describe something you notice about the coordinate pairs of even functions and something you notice about the coordinate pairs of odd functions. In case you were wondering, some of the graphs are strikingly similar, aka they are the same. 2, 3, 4, 5, 6, 7. I believe I added one additional graph. Yes, right. There's one additional function here for you to work through, right? So you should know which ones are even, you should know which ones are odd, and we're going to kind of come to a consensus on what the behavior is between the two. After you've done that, if we know that a function f is said to be even and f of 3 is 7, what can we say about the output of f of negative 3? And vice versa, if a function g is odd, what conclusion can you draw about its opposite coordinate or its opposite input? This is a slide that, yes, I know you may not remember doing this in Algebra 2, but I would like to kind of reinforce or reveal some of those previous memories. So we'll talk about that if that's something that was a bit confusing. Now, generalizing our observations from all the activities, what rule does even function follow? Remember that f of x is the output of the function, right? So for an even function, is the output equivalent to the negative output? Is it equivalent to the negative input? Is it equivalent to both the negative output and the negative input? Or is it the same? Okay, it doesn't move. Probably this one. But regardless of the one you select, please explain your thinking. So it is very important that you match up these graphs in a corresponding manner and really take a deep, conscientious look at what's happening. Like I said, we'll definitely do a review of this in person, but really think through. Let's get some really good explanations here. So as I said before, even degreed functions reflect over the y-axis. If I wanted to draw in the color blue, the graph from 0 to 5 for this function, if it were to be even, I would merely want to, see, when does it cross? It crosses at 2. Oops, that's already a bad drawing. It's going to hit at negative 3.4. Come back through. Oh, dang. That was close. Right, so blue corresponds to my even. I could do blue as well. Same blue as well. Right, blue is going to correspond to my even function clearly, or well, as best as possible. Not no Vincent van Gogh, but these two sides of the function are symmetrical. But what happens if we have an odd? So change your color, and you sketch to me what you think a odd function would look like. Remember that an odd function needs to reflect not only over the y-axis, but also over the x-axis. That should more or less kind of give you a framework of the end behavior of the function. So make sure you explain your reasoning. But now let's get into the mathematical or algebraic way of identifying whether or not functions are symmetrical. So let's say that we have this function g of x equals x cubed minus x. We would fill in our corresponding values. So negative 2 cubed is negative 8 minus negative 2, plus 2, so it's going to be negative 6. Negative 1 cubed is negative 1, plus 1 is 0. This is also going to be 0. This will also be 0. This will also be 8 minus 2, which is 6. Great. What does that really freaking tell us? Who knows? Even, odd, neither. Beats me. But maybe you'll have a better idea. If we've established that a function f is even, then we know that f of x is equal to f of negative x. What we mean here, my pen, is that the output at x equals a particular number, right? So at a particular input, it's going to be equivalent to the output at x equals the negative of that number. So it's opposite input. In this case, we can see that negative 2 and 2 have opposite inputs. As far as this information is kind of useless because it appears that the function is gliding along the x-axis between negative 1 and 1. So we might want to increase our table and use values like negative 3 and 3 just to see what might happen. You try it out at home on paper. But after you do so, right, you might be able to decide whether it's even or odd, or maybe it's neither. Tell me, what would the thought process be regarding how we can take a graphical representation and verify it algebraically? So what could we do to this equation in order to manipulate it to verify that either one of these formulas for an even function, like the one we see here, or an odd function are true? Let's take a look at what Ignacio has done. Right, so Ignacio is working with this function j of x, 2 to the x plus 2 to the negative x, and he substitutes negative x into the equation to determine if the function is even, odd, or neither. His algebraic reasoning is as follows. Right, he winds up with 2 to the negative x plus 2 to the negative x. That negative x is going to simplify, but if we take a look, this expression looks strikingly similar to that expression. Okay. So, in essence, it is visible that f of x is equivalent to, not f, j, is equivalent to j of negative x. Because when we've substituted the opposite of the original input, we still wound up with the same exact function. So what we're having here is a mirrored effect, that the function behavior is going to mirror itself for the opposite input. Thus, we can state that function k of x is even. Now, as far as Andrea goes, Andrea substitutes this into her function. However, I think she might be erroneously forgetting some parentheses, and that's leading to maybe some miscalculations regarding her arithmetic. She says that p of x is neither. What do you think? Please provide evidence below to your reasoning. Okay. So make sure you hit that math type button and maybe clarify Andrea's mistakes. So in this slide, we have a few different functions, and we're going to determine if they're even, odd, or neither. Remember, in order to determine that, we are going to substitute in the opposite input. So in this case, n of negative x, and we will substitute a negative x in any location that we see that awkward moment when someone gets to your house while you're in the middle of recording. So, as I was saying, right, we're going to substitute a negative x in for any location that we had an x variable, right, because that is our input. Negative x to the second power minus 4. But we're not looking to expand what we're seeing, right? If it's in factored form, leave it in factored form. We're determining whether or not the function will be the same or if it will be its opposite. So, as we can see here, we are going to, all of these squared terms will yield a positive. So let's copy and paste that. So we are going to have a function that looks strikingly similar, except for one distinct feature. But here's our original function, x times x squared minus 1 times x squared minus 4. Yet there's a negative out front. So what is happening is that the function n of x is equivalent to negative n of negative x, indicating that this function is an odd function. And like I said, it doesn't necessarily have anything to do with the exponents. Okay, they have some type of influence, but this term on the outside, this x, right, part of the original function, is what is creating the entire output of the function when we're looking at the negative x, the opposite of the input, where it's requiring it to have the opposite behavior both horizontally and vertically. So please do the same with k of x, determine if it's even, odd, or neither, and state whether or not the function is even, odd, or neither. And at that point, you might be sitting there, your brain pooling out of your ear. I understand this is a very difficult and conceptual style of thinking, but I have the utmost confidence in you, and fear not if it is something that you were struggling with. We are most certainly going to review this together in class. Make sure you go back and edit your answers after you've gained a little bit more of an understanding. And that's where we'll pause this video.